So by now we've stated mathematical induction, and we are considering it to be proven, even though we're not proving it until the end of the lecture, but we consider it to be available. So this is where we are now. So theorem 94 is available for use, and you already saw definition 95, and you did theorem 96 on your homework. That should have been a very short one. So let's just keep theorem 96 in mind. I want to keep this fresh since we're going to use it a lot. So things are less than the next of themselves. Okay, that should be we should be pretty happy about that being true. So if we are imagining that the next of something is what comes after it, and if we're imagining that x less than y means x comes before y, then yeah, things should be less than what comes immediately after them. Things should be considered to come before what comes immediately after them. Okay, good. And this one, so the way I try to remember this one is that if I see a less than and then a next, sort of together like this, no matter what the two things are, x and y, then I can merge these two symbols, less than and next, and they become this. So, I mean, it sounds like a really obvious statement, and why would I need a mnemonic to remember it? But I actually do. A lot of this stuff here looks obvious, like, I don't know, I mean, most of the stuff we're proving most of these things are just sort of taken for granted so frequently that we cannot imagine things being any other way. And believe it or not, that actually makes the proofs tricky. There are a lot of tricky proofs here. Tricky not because the concept or the thing being proven is complicated, but because we're so early on in developing these ideas that we have very few tools actually available to us. So tricky just because of how little there is that we can use when we prove these things. The further you go along, the further down you go, you'll find that, you know, as these theorems become available, especially this one, when this one becomes available, and then this one, things will get easier. So as you do these exercises, more will be available, and that will make things easier, but also harder because more is available. So there are more possible solutions. All right, so right now we are early in that trade-off where very little is available to us. So there are not many solutions. So if there is one, we're more likely to find it since there's not more than one. But also, it's hard because there's not much available for us to use. So this is the theorem we're going to start with in this video about zero. So anything you want to know about zero, it's probably going to be here. One thing that's interesting about the title is we actually already have, technically, we already have a section, an entire chapter of the notes that's all about zero, right? Which is this one. Since zero is the empty set, this is technically all about zero. I mean, after all, zero and the empty set are just two names for the same thing, right? But that's not really what's meant when we say about zero down there. When we use the symbol zero, it's communicating an intention to be in a certain context. So even though in our sort of unified framework where everything is a set, zero and the empty set are two names for the same thing, when we call it zero, we are sort of thinking of something different, but not in the sense of, not in any sense that's internal to the language that we're developing, but in sort of a meta sense. When we say zero, we're referring to something that we're thinking of as being in the context of its next, and the next of that, and the next of that, and this set of what we're calling natural numbers, and also the ordering that it comes with. So all of that context is what we're pulling in when we talk about zero, rather than just thinking of it as the empty set. That's why the theorem about zero involves those kinds of things, next and the ordering. So now I want to go to prove the first part of theorem 97 about zero, which is if n is a natural number, then zero is less than next to n. And so our goal I mean, this is an if-then. So your instinct probably is to say, start with assume n is a natural number and then try to prove this, which is a very good instinct to have developed by now. But now that it's a strong instinct, I'm going to tell you that it's actually the wrong thing to do here. If you fix a natural number n, you're going to have a lot of trouble proving that this is true for your fixed natural number n. That's just because it's hard to prove things about natural numbers just using the definition, right? If you just go ahead and try to use axiom 5 using the fact that n is a natural number, well, then you're stuck with this very abstract definition. And yeah, you can make some use of that, but it's going to be a lot of work either making use of this or trying to directly use theorem 93. That work has been done for us by mathematical induction. And so really, our goal is to prove that for arbitrary n, for all n, if n is a natural number, then 0 is less than next n. And we do not do it by our usual universal generalization argument where we try to prove this by universal generalization. We're not doing that. Instead, the correct approach is to use mathematical induction. So this gives you a mechanism for proving that for all n, if n is a natural number, then and then insert whatever you want here about n. In this case, what we want is 0 less than next n. So I'm about to look into how to apply mathematical induction to prove this. But first I want to look at how do you prove this for specific natural numbers if you wanted to? This is a useful thing to consider because it sort of suggests to you how you might ever think of using mathematical induction. If you didn't already know that that was the right approach, how might you get a hint that, oh, this might be actually a good way to do it? So let's start sort of with a blank slate and then just think about proving 0 is less than next and then various natural numbers here. So this is our ultimate goal, right? For all natural numbers n, 0 is less than next n. But allow me to write something horrible, just for the sake of explaining something. So in some sense, what we want to prove is 0 less than next 0, and 0 less than next 1, and 0 less than next 2, and here comes the horrible part, and ... So this is something that should never actually show up in your proofs, since we don't have any formal rules for how to manipulate ... It means different things in different contexts, and we haven't even given it a real meaning, so it just has no role to play in our proofs. But I'm putting it here because you know what I mean, and this is not really a proof, but a meta discussion about how we might prove certain things. So the idea is you need to prove this, and you need to prove this, and you need to prove this, and so you'd need to prove an infinite collection of statements, which, since you have a finite lifetime, you cannot prove an infinite collection of statements, right? But let's just try and see what it looks like when we try. And you'll see sort of the idea of mathematical induction being suggested in the attempt. That's usually how it goes in practice. You try to prove something, and then you find that mathematical induction creeps its way into your attempt, and then you go and revise your attempt. So let's start with 0 less than next 0. Okay, so my first thought when I look at this is, oh, let me break things down in terms of the definitions of everything. So less than, well, that's like a membership, right? It's just a fancy way of writing membership. And next, well, that's 0 union singleton 0. And then I would think about what is this union, is 0 in there? And yeah, you can see a way of doing it, but I actually do not recommend this approach. And this is an easy way to quickly overcomplicate things. Instead, remember that mnemonic. If you have a less than and then a next, then those mush together and become a less than or equal to. So that is theorem 96 part 2. So you see how that's superior to sort of breaking down the definition of less than and the definition of next? That's why this is called the essence of less than and next. It's the essence. This is what we should use rather than the definitions whenever we can. This will really help simplify things. It's extracting what is important about those definitions. So this thing that we'd be trying to prove here is equivalent to 0 is less than or equal to 0. That's by theorem 96 part 2. Something less than next something is the same as something less than or equal to thing. And do we have 0 is less than or equal to 0? Yes, remember less than or equal to is literally defined to be less than or equal to. Do we have 0 less than 0 or 0 equals 0? Yeah, axiom 1 is 0 equals 0. Okay, great. So we have 0 less than next 0. So that's one out of the infinity things we have to prove. Pretty good progress. Here's 2 out of infinity. 0 less than next 1. So how would we prove this? Well, it's equivalent. Again, you see the less than in the next. So it's equivalent to 0 less than or equal to 1. And, well, back here we had, this was equivalent to 0 less than or equal to 0, which we have by axiom 1, right? We have 0 equals 0. But why do we have this? Why should we have 0 less than or equal to 1? Well, there are 2 ways to prove 0 is less than or equal to 1. We could either prove 0 is less than 1 or that it's equal to 1, right? Since, less than or equal to is literally just less than or equal to. So which one do you think we'll be able to prove? Or do you think either might be the case in different situations and we need to do a proof by cases of some kind? Well, I think that we're probably not going to have much luck proving that 0 equals 1. Especially considering that we earlier had an exercise that literally says prove that 0 does not equal to 1. So I'm going to say probably, so we can prove this. Probably if we're going to prove it in any way, then we will prove this by proving 0 is less than 1. Right? So we have 2 options to prove this, prove less than or prove equal to. Less than is probably the one that's going to end up working. But this, 0 is less than 1, this is, well, remember, 1 is the same as next 0, right? That's the definition of 1. So let me just point that out. We will do this by proving 0 is less than 1, which is next 0. Now this is equivalent. Here it is again, less than next. This is equivalent to, so less than next becomes less than or equal to. Oh, actually, you know what? We've already got 0 less than next 0. There are a couple of reasons we have it. One reason is right here. Things are always less than the next of themselves. But another reason is written right here. We already proved it. It was one of the previous things. So this is 0 less than next 0. We have this already. It's here. Let me make that a different color. It's over here. Okay, let's do another one. How about proving, so that's 2 out of infinity down. How about proving this one and getting ourselves to 3 out of infinity? Maybe we'll eventually get there. So I'm trying to prove 0 is less than next 2. Now I'm getting tired of writing down the same statements. So how about I just copy and paste this and see how much can be duplicated. and see if I can fix it so that it works. Let's get rid of this arrow, giant arrow. Let's see, 0 less than next 2. So that's equivalent to 0 less than or equal to 2. That's thanks to over here. And we will prove this by proving, well, we could either prove 0 equals 2, or we could prove 0 is less than 2, right? Probably 0 is less than 2 is the way we're going to do it. So 0 is less than 2. 2, by the way, is the next of 1, right? That's the definition of 2. Oh, we do actually have this already. 0 is less than the next of 1. It's right here. So did you see what just happened? I just copied the same argument and then changed a few numbers around. Let me color code which numbers changed. So we had 2 here, 2 here, 2 here, and 1 here. Everything else was the same. Oh, and the arrow points to a different statement. It points to the 1 right above. How about another one? So now I can literally just copy, right? I hope it's starting to become clear that I'm just copying every time. And then just go change these numbers into 3s. So we're trying to prove this, but we can do this by proving 0 is less than 3. 3 is by definition next 2. Oh, but we have already proven that 0 is less than next 2. It's here. Here's another one. And another one. And, you know, I could keep doing this all day. And I'll never be finished, but the whole approach is so systematic that it should really feel to you like the fact that I'm just repeating the same pattern throughout means, in some sense, I should just believe that all of these are true, right? Like, I'm just copying each time, right? So I believe 0 is less than next 0, 0 is less than next 1, 0 is less than next 2, and so on and so on and so on. And my belief doesn't just continue because I think that once I've seen enough examples, it must be true for everything. That's not mathematical induction. That would be called scientific induction, which is pretty different from mathematical induction. So it's not just that, oh, I see, you know, one black sheep and another black sheep and another black sheep, and all my life I've only seen black sheep, so I generalize to conclude that all sheep are black. No, then it would not be a certainty that all sheep are black, right? There could be a white sheep that I just haven't seen. That's scientific induction. Mathematical induction is saying, look, this argument that each one of these statements is true seems to rely on the previous argument, and the form of the argument is exactly the same every single time. And so it does end up being a mathematical certainty that all of them, all infinitely many of these statements with the yellow number changed every time, are going to end up being true. The thing that powers that is this theorem, Theorem 94. That's what it's enabling us to do. So pay attention to one thing about this sort of repeating argument. So you can see it's going to be the same each time, right? All of these are the same, except one looks different. That's this one. The argument here is different, right? The first argument tends to be different from the arguments that come after. One reason that's not too surprising is that these arguments rely on the previous ones, right? Each one of these relies on what came before. But the first one doesn't have any previous ones to rely on. It doesn't have any previous results to build its pattern off of. So it just has to stand on its own somehow. So here this one stands on its own because 0 equals 0. But usually it'll be different. This is the base case. This is why we have a base case and an induction step. The base case is this first argument that stands on its own. And then your induction step is going to be a sort of argument pattern that can be duplicated forever And mathematical induction is a theorem that says that if you have the top of that ladder, if you have, or the bottom, whatever you want to call it, if you have a base case, that first argument that stands on its own, and you have this argument building machine where you can duplicate forever from there, then you have your general result. Okay, now finally, let's actually do it. So usually you wouldn't do this, but if you ever did find yourself doing this, then that's a pretty strong signal that you should probably use induction. Here, this is not using induction, right? This is just foolishly trying to prove infinitely many things, which we will never have time to do. Now let's actually use induction. So this is my goal. So when I use induction then, when I use this theorem, the theorem is going to give me this as a conclusion, right? So I need to match the form of this. You know, what I get to choose when I'm using this theorem is the phi. That's the main thing that I get to choose, is the phi and the variable that plays the role of x. So it just comes down to basically choosing phi. So I'm trying to match the form of this here, the thing that I want, the goal that I want, with what induction will provide. So I'm trying to prove all natural numbers. So okay, let me look here. So we're trying to prove for all natural numbers n, this thing is true. So this thing is going to be the phi here, right? But notice that phi has this variable x that's getting replaced by different things in different positions. So the x, I sort of think of the x as the blank, or the slot where different things get replaced. So here, what's going to be our phi is 0 less than next x. That's our phi. So that our goal is proof that for all natural numbers n, 0 is less than next n. This is then phi with x replaced by n, which is what it's supposed to be here, right? Phi with x replaced by n. So this is our phi. There's nothing crazy special about the variable x, it's just the variable I happen to use in the statement of this theorem. And I just wanted a variable that's different from n or m or anything like that, so that it looks like sort of some special thing that serves as a blank that can be replaced. Okay, and are you seeing what the x stands for when you look here? The x stands for all the yellow numbers that I kept erasing and replacing for each one of these different copies. Every time I copied and pasted, I would replace a certain yellow number. That's sort of what that x is, the position that keeps getting replaced. So it's good to be very clear about what your phi is when you apply mathematical induction. So let me do this for the reader and for myself as the writer of the proof. We will prove by induction that for all n, if n is a natural number, then 0 is less than next n. So I'm going to keep in mind in my scratch work that phi here is 0 less than next x. Now that I've been clear on what phi is, I can choose any phi I want when I use mathematical induction. If I just follow this to the letter, then I can't go wrong. Okay, now there are two things I have to show. There's the base case, and there's the induction step. So these are the two parts of the proof. So looking here, base case means prove number 1, and induction step means prove number 2. Then mathematical induction lets me finish. Looking over here, base case means prove this beginning of the ladder, and induction step means prove that it's possible to step from one position to the next, that it's always possible to step from one position to the next. Okay, so let's write what we must prove. We must prove basically phi. So the base case will be phi with the x replaced by 0, and the induction step will be phi, but with the induction step is more complicated than that. The induction step will be for all n, if n is a natural number, then, and then what we have to prove is a big implication, right? That phi with x replaced by n implies phi with x replaced by next n. Okay, so phi replaced with x replaced by 0, that's 0 less than next 0. So we must prove 0 less than next 0, and we already had an argument. I'm just going to copy it over. So the argument was this is equivalent to 0 less than or equal to 0 by theorem, something I need to look up. Right, 96.2. Which we have since 0 equals 0. So that's it for the base case. Now for the induction step, suppose, okay, so what do I have to do? I have to prove this for all n. If n is a natural number, then blah, 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 blah. So how do I do that? Universal generalization. This is what we prove using universal generalization. So when you're using induction, you don't prove this using universal generalization. You prove this by referencing the theorem, Theorem 94, mathematical induction. What you do prove using universal generalization is the induction step. This universal is what you prove, rather than directly trying to do this one. And yeah, I know this looks more complicated, but this is typically a lot easier. It's allowing you to assume more, right? It's allowing you to assume this stuff. Okay, so I get to assume n is a natural number. Suppose n is a natural number. And I get to assume that I'm on a certain sort of position in this ladder, that I've already got the previous one, right? Each of these arguments ended with, oh, we had that already, it was back here, the previous one. So I get to assume that I already have the previous one when I do my induction step. So that's this, because I'm trying to prove this implication. So I'm assuming this, or pointing here. That's this. Let me write that in green here, or how about sort of running out of colors to use. How about I use red? You'll see why. This is kind of a special moment here. Suppose this is true and 0 is less than next n. Now our goal is to prove, what does this say? Phi with x replaced by next n. That would be 0 less than next n, right? So now we must prove 0 is less than next, and then what's replacing x is next n. Okay, and now I'm basically going to duplicate this argument, but for the last time. I'll never have to copy it again, since I'm sort of making this argument with arbitrary variables in place of the yellow numbers that I kept replacing. So instead of a 2 here, there will be an n, and instead of a 3, there will be a next n. So you see, I'm trying to prove 0 less than next n. Okay, I actually was lazy and literally copied that argument over. And now I'm just going to change things to make it work. So just replace these guys. So we're trying to prove 0 is less than next n, and less than next of something, thanks to this one, becomes just less than or equal to. So this is equivalent to 0 is less than or equal to next n. That's what's inside here. And then we'll prove this by proving 0 is less than next n, which, I don't need to do this part. That was because I was replacing the symbol 3 by next 2, which is the definition of 3. But right now, what's written already has this form. So we will prove 0 is less than or equal to next n by proving that it's less than next n. Oh, we have this already. It's here. It's the thing in red. It's the thing I got to assume over here. So let me put that in red. And now finally a concluding sentence. So by induction, so in other words, by theorem 94, by this theorem, I can now conclude this. So by induction, we have basically the goal, this. Okay, and we are done with this proof. So we've proven that 0 is less than the next of any natural number. That's pretty nice. So I wanted to highlight this red thing because it has a special name. Sometimes you want to refer to it, and you can't just point arrows like I'm doing. I can do this because it's like a board, a whiteboard or whatever, right? But people don't just point arrows over at things. Sometimes they number things. So this will be like displayed in a centered thing, like in your LaTeX, it'll be centered and it'll have a number next to it and label. And they'll say like, oh, we already have this, we have this by, and then they'll just put the number label. Or this actually has a special name. So this, whenever you're doing induction, this thing that you get to assume, the fact that you have the previous step and you're trying to prove the next step, this assumption that you have the previous step is called the induction hypothesis. Hypothesis is basically another word for assumption. So this is like the assumption that you are making for the sake of induction. So it's called the induction hypothesis. So in the statement of mathematical induction, that's this thing that you get to assume when you're trying to prove this. So that's called the induction hypothesis. And I want you to notice that we followed this format, right? It's like we're proving all natural numbers are green, except instead of n is green, we had 0 is less than next n, right? But other than that, we basically followed the format here. All right, so we were working on a pretty specific result here, some specific fact about 0, but this is a really good, looking at this and looking at this attempt at the same time, this is a really good introduction to induction. So this is like the most detailed that I'll ever go on how to write a proof by induction. So I would say this is the lecture to come back to if you later find yourself confused about how induction works in the first place, because we're going to use it a lot. It could be that between now and the time that you're using it, in a couple of weeks, you'll probably still be writing some induction proofs for this course. If by then you've forgotten things, I would say this is the lecture to revisit. Of all of them, this is the one.